Okay, in this tutorial we're looking at section 6.4 on dynamics. So Newton's laws of motion. Hey, we should be all pretty familiar with Newton's laws by now. And his first law is every body continues in a state of rest or uniform motion in a straight line unless acted upon by a net force. Newton's second law is the resultant force acting on a body is proportional to the rate of change of momentum. Okay, so that's a little bit of a different wording of Newton's second law, but essentially it's our F equals ma law. Okay, Newton's third law, for every action there is an equal but opposite reaction. Okay, momentum is denoted by P, and P is equal to mv, okay, where m is our mass and v is our velocity. Now units for momentum are kilogram meters per second, or kgms to the power -1. Okay, so we'll have a bit of a look at worked example 12. Okay, so we want to find the magnitude of the momentum of a car of mass 1.4 tons moving at 72 kilometers per hour. Okay, well, P equals mv. Okay, but m equals 1.4 tons. So m equals 1,400 kilograms. Okay, our velocity equals 72 kilometers per hour. To convert velocity from kilometers per hour to meters per second, we divide by 3.6. So 7.2 over 3.6 gives our velocity of 20 meters per second. So then we can simply just sub in P equals 1,400 times our velocity of 20 meters per second, which gives us a momentum of 2,800 kilograms meters per second. Okay, so we'll keep moving on. So resultant force. Now this is going to drives me out the wall, and it's going to drive you out the wall as well. Okay, saying that our resultant force, okay, is R equals ma. I know in physics we use F equals ma. Don't ask me why they've decided to use R, but in all the examples they use R. Okay, the resultant force is proportional to the rate of change of momentum. So we can say that it's proportional, or we can put in this K, which is a constant of proportionality, and say that R equals K times the rate of change of momentum with respect to time. If you do a bit of calculus on that, that's how we end up with our R equals ma formula, where m is the mass and a is acceleration. Okay, I don't know why they've used R. Okay, but we'll have to go with it. Okay, so worked example 13. Okay, a particle of mass 2 kilograms. Okay, so we've got m equals 2 kilograms on a smooth horizontal plane is acted upon by 3 forces in that horizontal plane. Okay, F1 has a magnitude of 8 newtons and acts in a direction north 35 degrees east. Okay, so we're getting our coordinates, well, our directions given to us in sort of our north, south, east, west directions. Okay, so we're north 35 degrees east and a magnitude of 8. So we're going to go this way, that's 35 degrees, and it has a magnitude of 8 newtons. Okay, F2 has a magnitude of 6 newtons and acts in the direction south 20 degrees east. That's south 20 degrees east. Magnitude of 6 newtons, and it was 20 degrees. Okay, F3 has a magnitude of 7 newtons and acts in the direction of west 40 degrees south. Okay, so we're going to be over this way. We're saying that's 40 degrees. Okay, and that has, oh no, sorry, not that side. So this side, 40 degrees. And it's got a magnitude of 7 newtons. Okay, if I is the unit vector of magnitude 1 newton acting east, j is the unit vector of magnitude 1 newton north, find the magnitude of the acceleration of the particle. Okay, so we've got our force diagram. We need to resolve our forces, all our forces into their components. So this was F1, this is F2, this is F3. So F1, okay, is going to equal 8 sine of 35 degrees I plus 8 cos of 35 degrees J. Okay, we can say, well, F2 is going to be 6 sine of 20 degrees I plus 6 cos of 20 degrees J. Okay, and F3 is going to equal minus 7 cos of 40 degrees I, simply because we're going back in this direction now. Okay, and sorry, yeah, for the same idea, sorry, that should be a minus because we're going down. Okay, minus 7 sine of 40 degrees J. Okay, this one we switched our sines and our coses because our angle is over this side. If our 40 degrees was in here, okay, then we would have been saying that it was the other way around, but that doesn't matter too much. So we know the resultant force equals F1 plus F2 plus F3. So our resultant force is going to be so if you like, what we'll do is we'll just combine all of our i's and all of our j's together in this step. So we'll say that we've got bracket 8 sine of 35 plus 6 sine of 20 minus 7 cos of 40 I, okay, plus 8 cos of 35 minus 6 cos of 20 minus 7 sine of 40 J. Okay, so there's quite a bit of work there. Okay, but when we do that, okay, we find that when we actually work out all of these and bring them together, it's 1.278 I. Okay, and then when we work out what this value is, it becomes minus 3.584 J. So each one of those bits, it's just a calculator step. You just whack it in the calculator and work it out. Okay, we know M equals 2, and we know that R equals MA. So A is going to equal R over M. Okay. So what that means, and we know that M equals, that R equals our, scratch out. We know M is 2, so R equals 2A. Okay, what we need though is our magnitude of A. So what we've got now, so we'll rewrite that, okay, and say, well, we know that this is 2A, so A, okay, is going to equal half of each of these, so it's going to be 0.639I minus 1.792J. Okay, so we just know that R equals MA, M equals 2, so R equals 2A, so we're saying 2A can equal all this, which means 1 lot of A equals all that. We need a magnitude of A, okay, because we don't know what it is yet. We've just got to do Pythagoras' theorem on this and say, well, it's 0.639 squared plus minus 1.729 squared. Okay, when we get that, it's 1.90. Okay, so the acceleration equals 1.90 meters per second squared. Okay, is what we need to do there. So we'll keep moving on. Okay, we need our constant acceleration formulas. Okay, anyone that's done physics will know what they are, or hopefully know what they are by now. So we've got V equals U plus AT, S equals UT plus a half AT squared, S equals a half U plus VT, V squared equals U squared plus 2AS, and S equals VT minus a half AT squared. Okay, so U is our initial velocity, V is our final velocity, S is our displacement, A is our acceleration, T is our time. Okay, if we talk about motion on inclined planes, okay, then we've got to resolve our forces into their components. Use the net force acting down the plane as the resultant force in R equals ma, and note that R will usually equal mg sine theta minus ff, where I said ff is our frictional forces. Okay, so we're just going to go through and do a couple of different worked examples here. So a boy of mass 63 kilograms is on a skateboard of mass 2 kilograms. And he's freewheeling on a level track. His speed decreases from 10 meters per second to 5 meters per second as he moves a distance of 30 meters. Find the magnitude of the resistive force, which is assumed to be constant. Okay, so what we're saying is we've got a kid on our skateboard. Okay, there's going to be a normal force acting this way. There's going to be a weight force of, it'll be 65g because he's 63 kilos plus the 2 kilograms of the skateboard. Then we're going to have some frictional forces. Okay, and we're saying that this is the direction of motion. So he's actually going this way. Okay. So what we need to do is we need to go, okay, what information do we know? Okay, and this is always the way you should be approaching these questions. So we know our initial velocity is 10 meters per second. We know our final velocity is 5 meters per second. Okay, we know S equals 30 meters. Okay, and we're trying to find A. That's what we know. Okay, T, we don't know. Okay, so we look at our formulas and see which one we could use, and we can use V squared equals U squared plus 2AS. Okay, so V squared is 5 squared equals U squared, which is 10 squared, plus 2 times A times 30. Okay, which means we end up getting 25 equals 100 plus 60A. So 75 is going to equal, so minus 75 is going to equal 60A. So A is going to equal minus 1.25 meters per second squared. Okay, so we need to find our resistive force, or our frictional forces. So we know that R equals ma. Hey, we know that our mass is 65 kilograms. Our acceleration is negative 1.25, right, which means we get minus 81.25. Okay, the negative just means we're going in the opposite direction to our motion. Okay, so our resistive forces equals 81.25 newtons. Okay, so not too hard of a worked example, that one. We're going to have a look at worked example 16. Okay, so a boy of mass 70 kilograms rides a 10 kilogram bicycle up a slope of 1 in 5. Okay, if the resistance to the motion is 1/4 of the weight force, find the tractive force of tyres when he ascends with an acceleration of 2 meters per second. Okay, so we need to draw a force diagram for this. So this one just is worded a fair bit differently to ones that we've seen in the past. So we know we've got an angle theta. Okay, we've got our kid on a bike. Okay, that's going to have a weight force of mg. Okay, we know we're going to have a frictional force, which we're calling a resultant frictional force. Okay, we know we're also going to have a driving force up the hill. Okay, and we know we're going to have a normal force as well. Okay, so we need to resolve the force upwards in the direction of motion. Okay, and we know we're accelerating at 2 meters per second squared. Okay, up the hill, up this way. Okay, so we need to resolve the forces upwards in the direction of motion. So the boy and the bike move up a slope with an acceleration of A. Okay, so we know we've got our driving force minus our frictional forces. okay, minus, now remember from previous tutorials, the part going up this way is going to be mg sine theta, so mg sine of theta, okay, and that's going to, so that's our sum of our forces, okay, and that's going to equal our mass times our acceleration. Okay, so we can say our force going up the hill has to equal our resistive forces plus our mg sine theta, okay, plus ma. Okay, so what we know is that RF is a quarter of our weight force. We knew that, so we can say that RF is 1 on 4 mg. Okay, we know we have a slope of 1 in 5, so we know that sine, okay, so a slope of 1 in 5 means that we're going it means that our sine of our angle is going to be 1 over 5. So we can then say that we've got plus 1 on 5 mg, okay, plus our ma. Okay, so then we know we've got F equals mg on 4 plus mg on 5 plus our ma. Okay, which means what we can do is we can do some cross multiplication, okay, and add our fractions together, and what we're doing is then taking out m as a common factor as well to give us m equals 9g on 20 plus a. Okay, the total mass of the boy and the bike is 80 kilograms and the acceleration is 2 meters a second. So we can put those in and say, well, we've got our mass of 80, and then we've got our 9 times, well, we know g is 9.8 over our 20, plus we know we've got an acceleration of 2. Okay, so when we do all of that, we get a force of 512.8 newtons. Okay, so that's the tractive force, or the force that he has to apply to accelerate at that speed. Okay, so we've got one more worked example to have a look at, okay, which is worked example 17. Okay, so we'll set up our picture first. So we're going to have an inclined plane again for this one. So a certain strap on a suitcase will break when its tension exceeds 10 kgWt. Okay, find the greatest acceleration with which a 12 kilogram suitcase, so we've got a suitcase here, our plane, inclined plane, that is 12 kilograms. Okay, we've got a smooth plane, so we can ignore our resistive forces this time at 40 degrees. Okay, and we also know that our strap is at 20 degrees to the plane. Okay, we know we're also going to have our weight force of 12g down. We're going to have our normal force at right angles here. Okay, so we need to find the component of the tension force up the plane. Okay, so we need to be careful here because we need just the part going up the plane, which is going to be equal to 10g cos of 20 degrees. Okay, the component of the weight force which acts down the plane is going to be 12g sine of 40 degrees. Okay, because we know up here, is going to be, I forgot to write that in, our 10g, okay, which is what in our question, our 10 kgWt is. Okay, so the suitcase moves up the plane with an acceleration of a. Okay, we know our mass is 12. Okay, so we know our resultant force is our 10g cos of 20 degrees. Okay, take away our 12g sine of 40 degrees has to equal our mass times our acceleration. So this is our resultant force. up the plane. So we've got this part, okay, this component of this force, okay, going up the plane. Okay, we have the component of this force going down the plane, which is this one here. Okay, and so that's our resultant force. Okay, we know that's equal to our mass times our acceleration. Okay, okay, so then what we can do is we can say that we need to resolve our forces perpendicular to the plane now. So we can say that we've got 10g sine of 20 degrees, so that's this part of this force, okay, plus our normal force, okay, take away our 12g cos of 40 degrees, that's going to equal 0. Okay, so we can solve to find the maximum acceleration. Okay, so what we're looking at doing, okay, so we've got this stuff here, okay, so they're just telling us about that because what we should be doing is always looking at resolving our horizontal and vertical components along our plane, okay, but in this example, we actually don't need this, okay, because we're only worried about our maximum acceleration. Okay, so what we can do is we can solve this part for A, because we know all our numbers now. So we can say A equals our 10 times 9.8 times cos of 20, take 12 times 9.8 times sine of 40, okay, all over 12. Okay, so I just wanted to include this step here because I have it in the worked example, okay, but you actually don't need it, and they say in there you don't need it for this example, but I suppose they just wanted to show you what the other components would be. So anyway, when we find our acceleration, it is 1.37 meters per second squared. So that's the maximum acceleration, okay, any faster than that, and we're going to break our strap. Okay, so that's the end of this tutorial. Hopefully that gets you through the questions you need on section 6.4.